Welcome to today's video. So this video we're going to talk about confusion matrix. As the name suggests, it's really confusing. In the view, what I had is a screenshot I took from Wikipedia page. That's the location where I went to try to understand the concept better. Is the table really informative? Yes. Is it really easy to remember? Probably not. So that's why I had the intention to try out different combinations to understand the terminology better. So for us, what we want is the first thing, we're looking at the yellow tab here, the actual values. So those are, I would say is more in like pure math sense, the population values. So usually this is in the back end, you never see the real world. If you know it, great, life is easy. If we don't, that's why you want to go out there to collect data. You collect a sample of the data. Then you want to use a sample estimator the two population parameters. On the top, we have the predicted conditions. So that's what the model performs as. Naturally, you can see if the leading diagonal, the green cells what we have, if a population is indeed a positive case, then you predict positive. Great, you did a good job. Similarly, if it's negative, you predict negative. That's good. So, for example, in quite often medical test, you test for do you have COVID? You do a test, do you have the disease COVID or not? So assume you do have a COVID, you do have symptoms, you do actually have virus, you do your test, turns out yes, test says you do have COVID. That's a true positive, doing a good job. Vice versa, you don't have COVID, you don't have symptoms, you don't have any virus, but why not? Just be safe, do your test. Turns out the result come back negative. Yes, it correctly captured the negatives. For us, in the machine learning, particular for the category variables, like the classification problems, is the off diagonal we will consider. So we can see here the false negative, false positive. So those guys are the type 1, type 2 error. Or in the statistical sense, you talk about hypothesis testing, your alpha and your beta. Relevant, you also have the power of a test. This sheet, it does give a lot of combinations, but for us, we actually concentrate only few of the measure mostly. We're gonna look at the table on top, but first we'll give a little bit more context for this dashboard. Given the simplicity of the dashboard, I set a bit limit in the backend. The number is 10,000 cases. We try to say, okay, we know the true values, so you can adjust the true parameters. Let's see how that affect the performance of the model. Then we can hopefully, using that method, understand our metric better. Can I implement all the conditions dynamically on the parameters? No, I cannot. So in some case, in the table above, you may get some negative values. Yes, you could implement more complicated logic to prevent those values happen. That said, let's have a look at the table itself to actually play with it. So we scroll up. That's the top of the top half. That's where the interactiveness is coming from. What we control, we have 3 parameters on top we can control to play with the dashboard. I set default 10,000 cases for the dashboard. Just make the number integer, it's easier to understand. Top left, we select is the true positive, so another terminology called prevalence, how common it is among the population that's the case. So for us, what we see is the data set is 10K, we have 60%, up to some small running errors in the drag job, we have 6,000 cases, so that's the actual positive. So the first parameter controls the marginal total for that value. Similarly, the second value is called predicted positive. So you can see I try to keep the terminology a bit more consistent. You have the actual positive versus predict positive. So the predict positive corresponding to the column level. So among 10,000 cases, how many my prediction gonna say it's gonna be positive? So you can see because we try to learn it, so we try to build the table in the reverse order. Usually, what we have, you have some kind of forecast, you have a training test set, you know the true positive, the true negative, etc., the inner part of the 2x2 Excel. you try to expand onto the marginal sum, we go the other way. So we can see how the number plays out. The third one is called like a positive match. My intention for that is, okay, you said we have 6,000 true positives. That's here. Now we predicted 6,500 positive cases. So you're gonna mismatch some numbers. The third parameter to start up with, let's say we stick with 100% first. That indicates our model, even though we predict 6,500, we're gonna always capture the actual positives. With that said, that decides the top left number. So among the 6,000, we're guaranteed to capture. Of course, we can modify our number a bit. For example, if we say, yes, let's drag it down to 90%. Then the number changes. Among the 6,000 cases, we captured 90% of the values. So that's done. We capture 5,400 of it. So that's how the setup we're going to play with. Now, with the context done, let's actually understand our numbers. There's a various metrics that's used. That's the most common choice people choose to evaluate classification problems. Prevalence, as indicated on top, that's how common the true positive case it is. It's literally reflect the parameter of your selection. Accuracy is the number, it's a ratio. It's the ratio for our correct decisions. So in this particular scenario, what we have is we have the leading diagonals. They adds up about 83% of the total cases. That's how accurate our data is. It is quite common. People choose a machine learning model to be the accurate. The highest accuracy, the better it is. But of course, there are some cases, particularly when you have a biased data set. Things is a bit different. That's why we want to pay attention to different metrics. So let's have a look about the next two metrics, the recall and the positions. First, let's talk about recall this value. What the recall does, if you hover on the two tips, you get the information. So this is looking at the actual positives, among them, how many you capture. This is in fact what the third parameter is doing here. So we're looking at our first row of data. We say, okay, let's just concentrate on the positive cases. Let's say how good your model is. So because in the backend, I set the parameter to say 90%, this is what the recall does. Real life, you may not be able to set this parameter. That is what this is actually reflecting. Do you often know how good your model is? Maybe, may not be. That's why you want to run a training test split to estimate those values. By symmetry, the next number, precision, is actually talk about from the predictive positive case. So previously is at the row level. Now you can see it's more in the column levels. So what we have, similarly, we're looking among the predicted positives. We say, okay, you give me a prediction. That's how good you are to capture your true positives. You can see the numbers are very similar concept to the recall. That's why it's easy to get confusing. Also added the alternate name. You have predicted values from the table below. People can choose to see whatever suits them best. But I think quite all common various machine learning model output, they try to choose recall positions, etc. in their outputs. Lastly, it's called the F1 score. So what F1 score does is you have recall. We're going to show later case, not extreme case. You sometimes recall position are not proportional. This is a very good case. They're very high, but sometimes one number is very high, the other very low. How do you find that kind of average for those two values? That's what F1 score does. It's a harmonic mean of the previous value. Specificity, which I cannot pronounce, corresponding to the bottom rows. It's more looking the negative cases where you have. Because when the classification, particular binary classification problems, it's always up to the user to define what's the true cases. For example, you can define not having disease as to be a true result to be the positive results, or you can say you do have a disease to be the positive. So it depends on the context. Today in the video, we're going to concentrate on the metrics in front. Everything looks great. That's one particular when your model is actually very close prediction value to the true value. But actually, it actually looks some variation on the data set. In this case, we say, oh, your true value is 60%, we'll predict 65%. That's reasonably close. In fact, we can drag our number to be even closer. Let's say we have 60.8. So you should expect to see all the metrics on the top row, they should change to even higher values for all the performance. Now, if we change, interestingly, to our value to this extreme, let's give a 15% say. What I indicate is, we'll get a negative value, so that's even out of the bound. Let's go 20%. So your model is to talk about, let's not worry about the last diagonal value. The concept is, even though you predict very close to 60%, you say, oh yeah, that reflects true population data. But in fact, we can say our model should do a very bad job. You are actually just capturing the wrong proportion of your true values. So in this case, we say, okay, what we have 60% of that case, so among 6,000 cases, we do a very bad job. We only capture 1/5 of the data, so at 1,200 cases. So even though you say overall, people tell you we should have 6,000 people pass the test, you say, sure, I'm supplying you 6,000 people that's pass. Next case, if we still increase our value a bit, that's how you play with it. We go for the other end of the extreme. Some of the most common case for machine learning is very edge case. So when you have a very skewed data. So when the data is very rare to happen. For example, we can see our true positive value, say 1%. Then we change our predicted value. Let's say we go 1.5%. So when your value is very close, you can see you get very high performance. Great. Even say we give a little bit of freedom, no model is almost perfect. Let's say we just do our model to be 90% accurate. It does a very decent job. It captures most stuff. But what do you see? Even with number being this close, the precision value is not as high as others. Remember what the precision is? It's the vertical columns. So among the predicted positives, how many correct capture? Because the events are so rare, even the few mistakes you have in it, actually proportionally, they represent a big value. So when you look at numbers, sometimes your number may be low, but can you afford it? Maybe you can, then you don't worry about it. It does depend on the context you're talking about. Because, for example, are you looking for not, you are more afraid of missing capture the data you want to capture, or you punish too much to the false positives. Next thing we can look, say, hey, since most thing is negative, why don't we just go cheat a bit? We can almost say our model, the easiest model, we're going to just flat out to say we're never going to predict any positives. If we look at the numbers here, you do have a very high accuracy. Yes, because what you did, you correctly capture the false negatives, the true negatives. They outweigh the proportion of the values. But in reality, what you have is there's something that's supposed to be positive, but in fact, it didn't capture any one of those. That's when things became serious. Because consequently, for example, you want to do a medical test, you rather particular some serious disease, you would rather the test to be false positive. So people say, oh, do I have disease? You do a secondary test to confirm it rather than missing disease, because often that may be life-death scenarios. So you do not want missing any of those positives. So you rather willing to compensate for that. The second scenario, we modify a little bit. rather than blank out to say everything is negative, we don't predict. We can still predict it. You can see we have a 95% accurate for our model itself. Even our prediction rate is 2%. So you say, hey, it's 1% true value, 2% is our predicted proportion. Our model is 95% correct. We should be doing a very good job. Not as good as you would think. Because now, if you look at the precision number, you notice it's actually a very low number. It's less than 50%. Precision is the vertical among the predictives. So yes, you do predict 200 cases here. Among those, are you really capturing the true positives? Turns out you really half-half, kind of coin toss-up. So in this case, sometimes you do tolerate that because it's false positive case. Sometimes you willing to do a secondary test to filter the numbers out. It's kind of like trade-off. The two diagonal, the type 1, type 2 of diagonal mistakes, usually it depends on context. Sometimes the false positive is more willing, more acceptable to have. So if you have low precision, high recall, maybe that's something you can tolerate. Or sometimes cases you may do the opposite. That's why if your business requires both cases, maybe you want to measure your model by F1 scores instead. Hopefully, this workflow to the dashboard to show there's a lot more to play in the backend, depends on how good your model is. It's maybe a bit misleading to look your only the metric without actually looking the underlying data itself. When the data is reasonably symmetric distributed or mostly center mean, and assume your model does a really good job, then yes, the metric tell you the very uniform story. But when your data is skewed, very rare case, so disease detections, fraud detections, or sometimes even customer churn, then you got to be really careful with how you interpret the measure and which measure to use in what scenarios. You may want to do some pre-data process, you want to do some sampling, either oversample, undersample, or you do some mixed sampling strategy to handle the low volume class. Hopefully this video gave you a little bit more insight into understanding the confusion matrix. It's a tough concept, that's why I want to build this dashboard myself, play with it and try to understand the concept better. The link for the dashboard will post below, so do click onto it, try the number a bit to see, and hopefully it make you understand the concept better.